we know from the fundamental course that there's a way for us to transform the mass conservation law in the integral form into a differential form, which is called the continuity equation, right? So let me just write out the continuity equation for you. The transform itself, I will not do it here again because we have done that in the fundamental course. Well, here, if written in in the index notation, it's something like this, right? Okay, so 2 comments. First, the continuity equation can be developed by analyzing a differential volume. If we pick out a very small control volume and we analyze it, say something comes in, something comes out, etc., we can directly get the continuity equation. Okay? So this is the first thing. The second thing, there's a corollary of the continuity equation, which is as below. It's like somehow you can put the d over dt inside, right? It's a little like that. So this equation is sometimes called the Reynolds second transport theorem. Okay, we can prove this. This is mathematics, so it's not so hard. D over dt of the left-hand side, according to RTT, is something like this. Let's make our life simpler and just write 1s instead of 3. Okay, so here, if we agree, if we suppose, let's say, if we assume the dV in infinitesimal volume doesn't change with time, then we can put this thing inside, right? We can put the time derivative inside. So let's assume that and do that. So it will become something like this. And here, the closed integral on the control surface, we can do what? Use the Gauss theorem, right? To make this integral into the integral on the CV of these things' divergence. So let's do that. This thing's divergence will be something like this: beta rho u and everything integrate on the control volume, right? So now we see that the beta rho here is taking the derivative according to t. But we see this is a product. So according to the derivative law of products, we can transform this thing to be what? To be 2 terms, right? So it will become something like beta times d rho dt plus rho times d beta dt. And here, what's the nebula? It's also essentially a differential operator, right? It's like taking derivatives. So here we have 3 terms, but we can treat it as a product. So this thing, we can also divide that into 2 parts. So what are the 2 parts? Let's say we treat the product of these 3 properties to be the product of beta times rho u. Okay, so beta is one thing and rho u is another thing. So this will give me beta times the divergence of rho u plus rho u times the gradient of beta, right? So it's something like this. Okay. So do you see something familiar in these four terms? Well, I think you should, because our continuity equation is just here, right? Do you see the continuity equation in here? I bet you do. You see d rho dt and the divergence of rho u, right? And this thing is multiplied by beta. So according to the continuity equation, what will this part give us? 0. Okay. So here, do we see anything familiar? Well, first, it has the same rho, right? We can pull out the rho. But what's inside? d dt plus the u times nebula, right? U dot nebula. What's this? Do you agree it's just the material derivative? So what's our result? This thing, which is the left-hand side, will be equal to the integral on CV of what? Rho, we pull it out, right? And here, in the inside, we have this thing, which is d beta dt. This finishes our proof, right? See, this thing is just this thing.